For this lesson, we're going to be making use of our work on derivatives to identify what are known as extreme values, and we're going to be specifying those extreme values on a given interval. So let's take a look at the subsection of a graph I've shown you here. And I say subsection because it's actually constrained between A and B. So I'm only showing you part of the cubic, in this case, cubic polynomial. If we are looking for extreme values, that means highest and lowest points, there's two ways we can think about that. We can think of the varying highs and lows as they occur, and those are known as local extrema, local maximums, local minimums. And when we talk about those, we talk about those on the open interval, A to B, meaning it doesn't include A, it doesn't include B. And then we also look for what are known as the absolute. Another term for this is global maximums or minimums. And in order to determine the globals, we also have to take into account the values A and B, which means we close the interval. We include the endpoints. So let's start off by looking for the local max and min points. Now, from our graph, we can see here that we have a local maximum here and a local minimum here. But what feature is it that allows me to identify those algebraically? And what we're going to be interested in here is slope. So I've already got that ready for us on the next page. The idea of our local extrema. And we can have many of these. We can have many local maxima, many local minima. Now in this case I have one local maximum and I have one local minimum. At these 2 points, you can see the slope of the tangent line is equal to 0. And it's worth mentioning, I'll mention it throughout this, so the thing we want to keep in mind, the slope of the tangent line is going to be equal to 0, but you need to remember that the slope of the tangent line corresponds to the derivative of the function. So when we talk about the slope being 0, what that really means is that we're going to take the first derivative and we're going to solve it for when is the first derivative equal to 0. So in this case we have those two values. These are known as local extrema. The slope of the tangent is equal to 0. The next thing we have to consider are absolutes, which would be what is in this graph, as I've shown it, this subsection of graph that I've shown it, what is the highest and what is the lowest point? And the highest point is right there. That's our maximum, and that's known as our absolute maximum. Our lowest point is actually right here, and that's going to be our absolute, and I was about to write max again. That's our minimum. And so we can only have at most one absolute maximum and one absolute minimum. And so you can see here in this case we had an absolute maximum at the endpoint. Here our local minimum turned out to be, and I just used the other term here, a global minimum, which is the same as an absolute minimum. So this could be both local and a global minimum. And then notice over here at the side, so in this case, this endpoint was not significant. And that can happen as well. We have to consider these endpoints, but it doesn't always mean that they're going to play any kind of part in these extrema, these maximums and minimums. Okay, so when we are looking for extreme values on a particular interval, first thing is just to remember there's a couple of ways that you might see your interval notation used to express the idea. To find these extreme values, we are going to first solve for f prime of x equal to 0 on the specified interval. And just to remind you, once again, that is the same as saying the slope of the tangent is equal to 0. The derivative is the same as the slope of the tangent. The first derivative is the same as the slope of the tangent. And then once I have found these x values, so once I've done this and I solve for x, then when I say evaluate f of x, that means I'm now going to sub my x values in here. And this, of course, I may get many values here for x. I'm going to sub each one in, and that is going to give me, these will give me the y values. So when I sub an x value into the function, essentially I'm finding the value of the function for that coordinate of x, which means I'm finding the y coordinate. Then evaluate f of x at the endpoints. Now if the endpoints are a and b, that means we're going to be finding f of a is equal to some value, f of b is equal to some value. So that's what we're finding out from there. So as you can see, we have a whole bunch of y values. So we found the y values from the local extrema, we found the y values from the endpoints, and now we are going to compare the results of all of these different values, and that's going to give us our absolutes, extrema. Okay, so we've got an example here to start. We're finding the extreme values of this not particularly nice looking polynomial. It's an order 4 polynomial. So the first thing we're going to do is we'll start off by looking at local, which means I'm going to need the first derivative. So the first thing I'm going to do is find f prime of x, and that is equal to 12x cubed minus 12x squared minus 72x, and then the derivative of this constant part is just 0. Now I can go ahead and set this equal to 0, or because I know I'm going to be setting it to 0, I'm just going to go ahead and factor it right in place here. I notice there's a common factor among the constants of 12, and I know among the variables there's an x. And then from that I end up with an x squared minus an x minus 6, and that's a simple trinomial which I can further factor as x minus 3, x plus 2. And now we are going to set f prime of x equal to 0. So I get 12x times x minus 3 times x minus 2 is equal to 0. Sorry, I said x minus 2. That should be x plus 2. And for that to be equal to 0, I end up with solutions. X is equal to 0, 3, or negative 2. Those are my 3 possible solutions. Now once I've done that, I really need to find out, well, what are these values? So I'm going to sub these. I'm not going to substitute them into f prime though. I'm going to substitute them back into the original. And so from here, I'm going to actually evaluate, for example, f of 0. Now f of 0 is quite easy. I sub that in here and I end up with 20. F of 3, when I do that substitution, you can see there's a bit of work involved here. It's non-trivial arithmetic, but I've got it worked out in advance, and f of 3 is negative 169. And finally, f of negative 2 is equal to negative 44. And these are y values. These are y coordinates. Okay, these are y values, so we're going to be comparing these because we are looking for, in addition to the fact that we've got these local extrema, and so you know what, I can go ahead and make a note of that right now. So therefore my local extrema, they are the points 0, 20 and 3, negative 169 and negative 2, negative 44. Now the other thing I need to do is I need to compare that to my endpoints. And so what are my endpoints? My endpoints occur at x equal -3 and 4. So what is f of -3 equal to? And if we go ahead and make the substitution, we end up with f of 3, -3 is equal to 47. F of +4 is equal to -44. And so my endpoints are actually -3, 47 and 4, -44. And now to classify this, I need to take a look at all of these together. And so let's look for the highest y value. And I take a look and it looks like my +47 is the highest of the y values. So that's going to be my absolute maximum. And -169, so I'll put that here, that is my absolute minimum. Now, what did the question ask for? The question said to find the extreme values. It actually did not ask for the extreme points or the coordinates. It asked for the extreme values themselves. So the correct conclusion for this question is, therefore, the absolute maximum is, what did I say? It's 47. And minimum is -169. The question itself asked for the extreme values. What are the values at the highest and lowest end? Now we had to identify the local extrema as part of that, but it's also very important that you answer the question that has been asked of you. And here's the graph of that particular quartic. And this is just the graph on the interval shown from -3 to +4. And so when we look at our absolutes, you can see there is my absolute minimum at -169. And the highest point on this graph occurs here at positive, and what was it, +44? No, not 44, 47. Okay, now we've got a more of an application type question. We're talking about the amount of light intensity on a point is given by this expression. So the question becomes, what is it we need to do in order to answer this question? We've got a rational function here, polynomial over another polynomial. There's the given interval. We've got the units, candela and seconds. Determine the times of extreme intensity. So at what times do we have extreme intensity? And what is the minimal intensity? So in order to do this, first of all, we're going to need to take the derivative. So I prime of t. So I'm going to go ahead and I'll use the quotient rule for this, which is going to be the derivative of the numerator. So that's 2t plus 2 multiplied by the denominator unchanged minus the numerator t squared plus 2t plus 16 multiplied by the derivative of the denominator, which is simply equal to 1, all divided by the denominator all squared. Some simplifying here is going to give me 2t squared plus 4t plus 2t plus 4 minus t squared minus 2t minus 16, all divided by t plus 2, all squared. And I take a look, 2t squared minus t squared leaves me a t squared. 4t, 6t minus 2t is plus 4t. Plus 4 minus 16 is minus 12, divided by t plus 2, all squared. And as I did in the previous question, since I know I'm going to be solving for this, I'm going to want to factor. And also maybe just to check and see whether or not anything divides out from this. So two numbers that multiply to give me negative 12 and add to give me positive 4 is going to be t plus 6, t minus 2 over t plus 2 all squared. That is my derivative, I prime of t, the intensity, the rate of change of intensity for any time t. So now I'm going to set I prime of t equal to 0. And so I end up with t plus 6, t minus 2 over t plus 2 all squared equals 0. Now, other than worrying about restrictions here, and in this case we have a restriction that t is not equal to negative 2, there's no way that this denominator contributes to this thing being equal to 0. So I'm just going to cross multiply that out, and I end up with t plus 6 times t minus 2 equals 0. So t equals negative 6 or positive 2. Those are my two possible solutions. But we're talking about times here, and we remember that our domain or our interval is from 0 to 14. And so this negative 6, we reject that solution because it's not in the domain. And so now that we know that t equals 2 is in the domain, we're going to sub that value. So we need to evaluate what it is at these various values. So I need to test I of 2. I need to go back to the original function. And when I go back to the original function and I substitute 2 in here, 2 squared is 4, plus 4, plus 16, that's 24, over 4, that's equal to 6. So I of 2 is equal to 6. Then our endpoints, one of them is at 0. So one of those, we sub in I of 0, and we end up with 8. And the other endpoint is at 14. And we sub in I of 14, and we actually get a value of 15. So when do we have extremes? So let's mark these off. So what's our maximum? Our maximum occurs here at t equals 14. And what's our minimum? It was actually our local minimum. And so, therefore, the times of extreme intensity are, let's see, this one is at 2 seconds, and that one was a minimum, and 14 seconds, and that one was a maximum. And here's the graph. Once again, I've generated this using software. And so on the interval, you can see that it starts here, the first endpoint. It actually has a minimum here at 2 seconds. So that's what we detected when we found the slope of the tangent equal to 0. And then it goes up from there. So the maximum is at this other endpoint. Okay, that's it for the lesson. As you can see, these are getting a little bit more involved in the sense that there's quite a bit more work you have to do. It's not just a matter of taking the derivatives. You have to actually make use of them and apply them. So be careful with these, and also make sure that you're taking those derivatives correctly, because if you don't do that, then everything's going to go wrong from that point forward.